To continue, I will relate our work to algorithm that compute the congruence closure of an equivalence relation. In fact, of a set of equations um, between terms not involving variables. Those two papers are quite well-known papers, and they propose algorithm to solve the equation between terms, and this is a decision problem. This is also a solution to the word problem on certain theory. And in fact, our method can be related to this algorithm, but the main difference is that instead of computing a congruence closure between all the terms in the equations and the subterms in the equation, in fact, we compute all terms that are equal to the term and the subterms in the equations. So we compute, we derive more information. And also for at the efficiency level, our method is competitive with those two, and especially with this one, which is more efficient than that the algorithm proposed in that paper. But we think maybe our method is still more efficient, although we have not a proof of that at this moment. But I will show you an experiment to convince you that our data structure is efficient. Okay. So we have in this example program, we first generate a very large expression, a very large term containing 100,000 symbols. Okay, you can see it's quite large. Okay, and of course this term is represented as a set of structures, many sets, in fact 39,000 sets of structure, and then we generate randomly equations between the subterms of this term. In fact, the subterms are represented by the identifier of their set of structure. So I can also show you, in fact, the actual equations between terms. Okay, that here you have the list of equations. And then we can solve the equation. In fact, we work on the set of structures, and we put together the set of the set of identifiers. So here is the result of the computation. You see that it needs only a fraction of a second to solve all the equations. Okay. And also, here we have the timing. Here we have the number of set unification. A set unification is when two sets are put together. Here we have the number of equations that are already solved. You can see that at one point here, one equation makes that a lot of unification are executed. It's because a lot of structures have the same key. And since they have the same key, they represent the same term, so the sets must be unified. Okay? And the time, the execution time is in fact proportional to the number of renaming of structures. Here we have the number of structure renaming, And you can see that this number is more or less proportional to the number of unification times the logarithm of the number of unification. Okay, here we have the number of structure remaining, and here we have the number of, no, that's the contrary, that's the number of structures, and that's the number of sets. At the end, there are only 18 sets and 100 some structures. Okay, so you can see that it works well, and it's promising for us at least. Now it's time to conclude. So in the future, we plan to improve our work, mainly the goal-oriented algorithm, which can be, I think, much improved. We will apply our method to other kind of expressions. We will compare more deeply and experimentally with the existing methods to compute the congruence closure. And also we intend to compare and to improve our work by using techniques used for term rewriting systems. Okay, thank you very much. Thank you for your attention. I hope that you will put some question on YouTube. Thank you.